Hello there! Tonight's gentle journey ventures into the vast darkness between stars to explore one of the universe's most beautiful and mysterious processes, the birth of stars themselves. Those twinkling lights we see scattered across the night sky like diamonds on velvet. Each one began its life in what astronomers poetically call stellar nurseries, cosmic cradles where gravity, dust and time conspire to create the very furnaces that light up our universe. Before we drift into these celestial maternity wards, I'd love to know where in the world you're watching from, and can you see any stars from your window tonight? Fitting, isn't it? A video about stellar birth, and here we are, perhaps gazing up at the very stars that were born billions of years ago in nurseries, much like the ones we're about to explore. If you find this cosmic lullaby soothing, intriguing, or just a nice way to unwind after a long day, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of calm reach others who might need a peaceful pause beneath the stars too. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something about how the universe creates its own nightlights before you drift off. So settle in, slow your thoughts, and let's begin, because somewhere between swirling gas clouds and nuclear fusion, dreams and daylight lies the story of how stars are born. Imagine, if you will, the space between stars. It's not the empty void you might picture, but rather a thin, delicate soup of gas and dust particles. Hydrogen mostly, with a sprinkle of helium and tiny grains of cosmic dust, no bigger than the particles in cigarette smoke. This interstellar medium, as astronomers call it, fills the galaxy like a gossamer web connecting star to star, system to system, and within this seemingly empty space lie the seeds of every star that ever was or ever will be. These stellar nurseries go by many names: molecular clouds, giant molecular clouds, nebulae, each term describing the same fundamental thing. Vast regions of space where gas and dust have begun to gather like cosmic cotton candy. Some of these clouds are truly enormous, stretching across hundreds of light years and containing enough material to create thousands of stars. Imagine a cloud so large that light itself, travelling at its maximum possible speed, would take centuries to cross from one side to the other, and yet, despite their immense size, these clouds are incredibly sparse. If you could shrink one down to the size of your living room, it would contain fewer particles than what most people would consider a decent vacuum. But within this near emptiness, something remarkable happens. Gravity, that gentle, persistent force, begins to work its magic. Wherever the gas and dust happen to be just a little bit denser than the surrounding space, gravity starts to pull more material inward like a cosmic whirlpool forming in slow motion. It's a process so gradual that if you could watch it unfold, it would make continental drift look like a high-speed chase. We're talking about changes that take millions of years just to become noticeable. The trigger for this cosmic choreography can come from many sources. Sometimes it's the shockwave from a nearby supernova, the explosive death of a massive star, sending ripples through space like a stone thrown into a still pond. Other times it's the gravitational dance of galaxies colliding, or the spiral arms of our own Milky Way compressing gas clouds as they sweep through space. Occasionally it's simply the random motion of particles in space bumping into each other, building up density little by little until gravity takes notice. Whatever the trigger, once gravity begins its work, the process becomes beautifully self-reinforcing. As more material falls toward the center of the cloud, the gravitational pull grows stronger, attracting even more gas and dust. It's like rolling a snowball down a hill, except this snowball is made of hydrogen and helium, and the hill is the curvature of space-time itself. The cloud begins to contract, slowly at first, then with gathering momentum. As the cloud contracts, something fascinating happens. It begins to fragment, breaking apart into smaller, denser clumps like a soap bubble, separating into smaller bubbles. Each of these fragments becomes a potential stellar nursery within the nursery, and within each fragment the same gravitational dance continues. Material spiraling inward, density increasing, temperature beginning to rise. This is where things start to get interesting. As the gas falls inward, it picks up speed like water spiraling down a drain. And just like that water, the falling gas begins to spin faster and faster. Conservation of angular momentum, the same principle that makes figure skaters spin faster when they pull in their arms, causes these collapsing gas clouds to rotate more and more rapidly. The spinning gas begins to flatten into a disk, much like pizza dough spun by a skilled chef. At the center of this disk, material continues to accumulate, forming what astronomers call a protostar. Not yet a true star, but a dense, hot ball of gas that's well on its way to becoming one. The protostar is surrounded by a swirling disk of gas and dust called an accretion disk. Material from this disk continues to spiral inward, feeding the growing protostar like a cosmic conveyor belt. During this phase, the protostar is hidden from view, wrapped in a thick cocoon of dust and gas, a cosmic chrysalis. The dust absorbs visible light, making the protostar invisible to optical telescopes, but it glows brightly in infrared light, heat radiation that can penetrate the dusty veil. This is why astronomers often use infrared telescopes to study stellar birth. The heat signature reveals what visible light cannot. As more and more material falls onto the protostar, its core becomes denser and hotter. The weight of all that gas pressing down creates enormous pressure, and with pressure comes heat. It's the same principle that makes a bicycle pump warm up when you use it, except scaled up to cosmic proportions. We're talking about pressures millions of times greater than anything on Earth, and temperatures that climb into the thousands, then tens of thousands of degrees. But the protostar faces a problem. As it tries to grow larger, the very process of accretion that feeds it also creates obstacles. The infalling gas carries angular momentum, which makes it want to spin rather than fall straight down. It's like trying to pour water directly into a spinning bucket. Much of it ends up swirling around the edges rather than falling to the bottom. This is why the accretion disk forms and why the process of stellar birth takes so long. The disk itself becomes a complex dynamic system with its own weather patterns and phenomena. Gas in the inner regions orbits faster than gas in the outer regions, creating shear and turbulence. Magnetic fields threading through the disk can channel material inward or launch powerful jets of gas outward from the poles of the protostar. These jets can extend for light years, carving cavities through the surrounding gas cloud like cosmic blowtorches. Meanwhile, the protostar continues to contract and heat up. Its core temperature climbs toward the critical threshold where something truly magical will happen. Nuclear fusion, the process that will transform this ball of collapsing gas into a true star. But we're not there yet. The protostar is still growing, still accreting material, still heating up, slowly building toward that moment when it will ignite and announce its birth to the cosmos. During this lengthy gestation period, which can last anywhere from a few 100,000 to several million years, the protostar goes through various phases. Sometimes it's relatively stable, steadily accreting material and growing larger. Other times it becomes temperamental, undergoing sudden bursts of activity that can make it temporarily much brighter. These outbursts, called few Orionis events after the first star observed to exhibit this behavior, can last for decades or even centuries. The surrounding environment is equally dynamic. The accretion disk evolves over time, with material gradually spiraling inward toward the protostar. Dust grains within the disk begin to stick together, forming larger and larger particles, pebbles, rocks, and eventually the building blocks of planets. This is how planetary systems are born, not as an afterthought to stellar formation, but as an integral part of the process. As the protostar matures, it begins to clear out its immediate surroundings. Intense heat and radiation pressure start to push away the remaining gas and dust like a cosmic wind. The powerful jets emanating from its poles carve out bubbles in the surrounding cloud, creating the beautiful structures we see in images of star-forming regions. Pillars of creation, cavities lined with glowing gas, and intricate lacework patterns of light and shadow. Slowly, gradually, the cocoon of gas and dust that has hidden the protostar begins to thin, as material either falls onto the star, gets blown away by stellar winds, or incorporates into the growing accretion disk. For the first time, light from the protostar begins to escape into space, not yet the steady, fusion-powered light of a mature star, but the glow of gravitational contraction, the potential energy of all that infalling gas being converted into heat and light. This is a crucial phase in stellar development. The protostar is approaching the moment when its core will become hot and dense enough for nuclear fusion to begin. The temperature at the center climbs past 10 million degrees Kelvin. At this point, hydrogen nuclei moving at incredible speeds begin to overcome their natural electrical repulsion and fuse together to form helium, releasing tremendous amounts of energy in the process. The moment when fusion ignites is both gradual and sudden. The nuclear reactions start slowly at first, just a few fusion events here and there. But as the core temperature continues to rise, the reaction rate increases exponentially, like a fire catching hold of dry kindling. Suddenly, the protostar has an internal energy source that can support it against gravitational collapse. The inward pull of gravity is balanced by the outward pressure of fusion energy. This moment marks the birth of a true star. The transition from protostar to main sequence star is complete. What began as a cold, diffuse cloud of gas and dust has become a nuclear furnace that will burn for billions of years. The new star settles into a stable configuration where gravity and fusion pressure are perfectly balanced, a state that astronomers call hydrostatic equilibrium. But the story doesn't end with a single star. Stellar nurseries are prolific birthplaces, often producing not just one star but entire clusters. Dozens, hundreds, or even thousands of stars can be born from a single giant molecular cloud, each following a similar path from gas cloud to protostar to main sequence star, but with variations depending on how much material they manage to accumulate. The mass of gas that a protostar gathers determines what kind of star it will become. Collect just a little material and you get a red dwarf, a small, cool star that will burn its fuel so slowly it could outlive the universe itself. Gather a moderate amount, like our Sun did, and you get a yellow dwarf star that will shine steadily for about 10 billion years. Accumulate a large amount of material and you create a blue giant, a massive hot star that burns through its fuel quickly and dies young in a spectacular supernova explosion. Some protostars never quite make it to true starhood. If they can't gather enough material to reach the critical temperature for fusion, they become brown dwarfs, failed stars that glow dimly from their own heat but never ignite the nuclear fires that would make them true stars. These cosmic also-rans drift through space like cooling embers, slowly fading over billions of years. The most massive stars, those born with tens of times the mass of our Sun, live fast and die young. Their intense gravity allows them to fuse not just hydrogen but heavier elements as well, creating the carbon, oxygen, silicon, and iron that will eventually become planets and people. When these giants finally exhaust their fuel, they explode as supernovas, scattering heavy elements throughout space and potentially triggering the formation of new stars in nearby gas clouds. And so the cycle continues. Stellar death feeds stellar birth. The heavy elements forged in the cores of dying stars enrich the interstellar medium, making it possible for new generations of stars to form with rocky planets orbiting around them. Our own solar system is the product of this cosmic recycling program, formed from gas and dust, enriched by countless generations of stars that lived and died before our Sun was even a glimmer in a molecular cloud. The stellar nurseries we observe today are forming the stars that will light up the galaxy for billions of years to come. Some of these newborn stars may have planets, and some of those planets may harbour life. Civilizations yet to be born may look up at their night sky and wonder about the stars, just as we do, contemplating the cosmic nurseries where those stars were born in clouds of gas and dust, not so different from the ones we've explored tonight. As we drift toward the end of our journey through these cosmic maternity wards, it's worth reflecting on the profound beauty of stellar birth. The fact that gravity alone, acting on the thinnest possible material, can create structures of such complexity and grandeur speaks to the elegant simplicity underlying the universe's most spectacular phenomena. Every star in the night sky, from the brightest beacon to the faintest glimmer, began its existence in a stellar nursery not so different from the ones we've visited tonight. Clouds of gas and dust transformed by gravity, time, and the fundamental forces of nature into the nuclear furnaces that make the universe shine. The very atoms in your body were forged in the cores of ancient stars that were themselves born in stellar nurseries billions of years ago. We are quite literally made of stardust. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created in stellar cores and scattered into space by stellar winds and supernova explosions to eventually find its way into new clouds of gas and dust, new stellar nurseries, and ultimately into us. We are not just observers of the cosmic story, we are part of it. Participants in the grand cycle of stellar birth and death that has been unfolding for over 13 billion years. So the next time you look up at the stars, remember that you're not just seeing distant suns, you're seeing the products of cosmic nurseries, vast stellar maternity wards where gravity and time conspire to create light in the darkness. Now where this cosmic story becomes even more extraordinary is when we consider what happens after those stellar fires ignite. You see, once our protostar has gathered enough mass and its core reaches that critical temperature of about 10 million degrees Celsius, something almost magical occurs. Nuclear fusion begins, and hydrogen atoms start fusing into helium, releasing tremendous amounts of energy. This marks the birth of a true star, transitioning from a dark, hidden protostar to a brilliant beacon shining across the galaxy. But here's where things get deliciously complex. Not all stars are created equal, and the mass our newborn star has accumulated during its formation determines its entire life story. If our stellar nursery produces a star with less than about 8 times the mass of our Sun, we get what astronomers call a low to medium mass star. These are the steady, reliable citizens of the cosmos. 6 billion years and has roughly another 5 billion years left in its main sequence lifetime. These smaller stars follow a rather predictable path through their lives. They spend most of their time in what we call the main sequence phase, steadily converting hydrogen to helium in their cores. As they age, they gradually become slightly brighter and hotter. Eventually, when they've exhausted the hydrogen in their cores, they'll expand into red giants, shedding their outer layers into space as beautiful planetary nebulae, leaving behind dense white dwarf stars that will slowly cool over trillions of years. But if our cosmic nursery manages to birth a truly massive star, one with more than 8 times the mass of our Sun, we're in for a much more dramatic story. These stellar giants are the rock stars of the universe, burning bright and fast. They consume their nuclear fuel at a prodigious rate, living intense but relatively short lives measured in millions rather than billions of years. They're so massive that their gravitational pull is immense, creating extreme conditions in their cores that allow them to forge elements far beyond simple helium. This is where the cosmic alchemy becomes truly spectacular. While smaller stars primarily fuse hydrogen into helium, these massive stars are like cosmic factories working their way up the periodic table. In their cores, helium fuses into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron. Each fusion process requires higher temperatures and pressures, creating layers within the star like a cosmic onion. The star becomes a nested series of burning shells, each producing different elements and releasing different amounts of energy. But iron presents a problem. Unlike lighter elements, iron cannot be fused to release energy. Instead, fusing iron actually requires energy, which means once a massive star's core fills with iron, it can no longer support itself against the crushing force of gravity. What happens next is one of the most violent and spectacular events in the universe. a supernova explosion. In a matter of seconds, the star's core collapses and then rebounds in an explosion so powerful it can briefly outshine an entire galaxy containing billions of stars. The temperatures and pressures during this cosmic detonation are so extreme that they create elements heavier than iron, things like gold, silver, uranium, and platinum. These explosions scatter all the elements the star created during its lifetime, plus these newly forged heavy elements back into space, enriching the interstellar medium with the raw materials for future generations of stars and planets. This brings us to one of the most profound realizations in all of astronomy. The calcium in our bones, the iron in our blood, the oxygen we breathe, and the carbon that forms the backbone of our DNA were all forged in the nuclear furnaces of ancient stars. Some of these elements were created during the long, steady burning of smaller stars, while others were born in the violent death throes of massive ones. We are quite literally made of star stuff, as astronomer Carl Sagan so eloquently put it. But the story doesn't end with stellar death. Those spectacular supernova explosions do more than just scatter elements into space. The shock waves they create ripple outward through the galaxy, compressing nearby molecular clouds and triggering new rounds of star formation. It's a beautiful cosmic cycle. Stars are born from the remnants of previous generations, live their lives creating new elements, and then return those elements to space, often triggering the birth of new stars in the process. Some of the most massive stars don't just explode and scatter their contents. If the core is massive enough, it can collapse beyond even a white dwarf or neutron star to form a black hole. These gravitational monsters are so dense that not even light can escape their pull. Yet even black holes play a role in cosmic evolution, influencing the formation of galaxies and potentially triggering star formation through their powerful jets and gravitational effects. The stellar nurseries themselves evolve over time as well. As stars form within a molecular cloud, their stellar winds and radiation gradually disperse the remaining gas and dust. The most massive stars, with their powerful stellar winds and eventual supernova explosions, can completely blow away the remaining material, effectively shutting down further star formation in that region. What was once a bustling stellar nursery becomes a sparse stellar association, with the newborn stars gradually drifting apart as they orbit the galaxy. Yet the cycle continues elsewhere. The heavy elements dispersed by dying stars mix with the primordial hydrogen and helium that still pervade space, creating new molecular clouds enriched with the products of stellar nucleosynthesis. These second and third generation star-forming regions can create stars with rocky planets, because now there are enough heavy elements available to form solid worlds, rather than just gas giants. This is how our own solar system came to be. Our sun is what astronomers call a population 1 star, meaning it formed from material that had already been enriched by previous generations of stars. The rocky planets like Earth could only form because earlier stellar generations had created and dispersed the silicon, iron, magnesium, and other heavy elements needed to build solid worlds. As we gaze up at the night sky, we're witnessing this grand cosmic story unfolding in real time. Every star we see represents a successful birth in some ancient stellar nursery. The fuzzy patches we can glimpse through telescopes, nebulae like the Orion Nebula or the Eagle Nebula, are active star-forming regions where new suns are being born even as we watch. In these cosmic maternity wards, the next generation of stars is taking shape, some of which may eventually nurture worlds where life could arise and evolve. The timescales involved in this cosmic drama are almost incomprehensible to human minds. The formation of a single star can take millions of years, while the main sequence lifetime of a star, like our sun, spans billions of years. The cycle of stellar birth, life and death plays out over cosmic epochs, with each generation building upon the achievements of the last. And so we find ourselves part of this magnificent, ongoing story. We are not separate from the cosmos, but intimately connected to it through the very atoms that make up our bodies. Every breath we take contains oxygen forged in stellar cores. Every beat of our hearts depends on elements created in cosmic furnaces. We are the universe becoming conscious of itself, made from the ashes of ancient stars, contemplating the nurseries where new stars are born. In the quiet moments before sleep, as consciousness begins to fade and the boundaries between self and cosmos blur, perhaps we can sense this deep connection. We are star stuff contemplating stars, temporary arrangements of ancient stellar material that have somehow learned to wonder about their origins. As we drift deeper into this cosmic journey, let's consider something truly extraordinary about these stellar nurseries. Each newborn star begins its life with a kind of stellar memory, carrying within it the chemical signature of every generation that came before. These aren't just random collections of hydrogen and helium anymore. They're enriched with the heavier elements forged in the nuclear furnaces of ancient stars, scattered across space by supernovae that occurred billions of years ago. Picture this gentle process unfolding. A molecular cloud, vast and patient, begins to stir. Within its depths, pockets of gas and dust start to clump together, drawn by the invisible hand of gravity. But here's where the story becomes particularly fascinating. These collapsing regions don't just fall straight inwards. They begin to spin slowly at first, then faster and faster as they contract, like a figure skater pulling in her arms during a pirouette. This spinning motion creates something remarkable. A flat, rotating disk of material surrounding the growing protostar at its center. This accretion disk becomes a cosmic carousel, with material spiraling inward toward the central star, while simultaneously flinging some matter outward in powerful jets. It's a delicate dance between creation and destruction, between gathering and dispersing, all orchestrated by the fundamental forces of physics. The temperature within these stellar nurseries varies dramatically depending on where you find yourself. In the outer reaches of a molecular cloud, temperatures hover just a few degrees above absolute zero, so cold that even hydrogen molecules can barely move. But as you venture closer to a forming protostar, the temperature begins to climb. The gravitational energy of infalling material converts to heat, warming the surrounding gas and dust until it glows with infrared light. This is why stellar nurseries often appear as beautiful, glowing regions when viewed through infrared telescopes. The Orion Nebula, perhaps the most famous star-forming region visible to the naked eye, reveals itself as a tapestry of warm, glowing gas punctuated by the brilliant points of newly formed stars. It's a cosmic nursery in full bloom, with stellar infants of various ages scattered throughout its luminous embrace. But not all protostars successfully make the transition to true stardom. Some, lacking sufficient mass, never achieve the critical temperature and pressure needed to ignite nuclear fusion in their cores. These failed stars, known as brown dwarfs, remain forever in a kind of stellar adolescence, glowing dimly from the heat of their initial collapse, but never achieving the sustained nuclear burning that defines a true star. They're the cosmic equivalent of a campfire that never quite catches flame, smouldering quietly in the darkness of space. The successful protostars, however, those that do manage to gather enough material and reach the necessary conditions for fusion, experience a moment of stellar awakening. Deep within their cores, hydrogen nuclei begin to fuse together, forming helium and releasing tremendous amounts of energy in the process. This energy radiates outward, creating the internal pressure needed to balance the inward pull of gravity. The star has found its equilibrium, its stellar voice, and begins its long journey through the cosmic symphony. The mass of a newborn star determines not just its brightness and colour, but its entire future. The most massive stars, those with 10, 20, or even 50 times the mass of our Sun, burn brilliantly but briefly. They're the cosmic equivalent of a spectacular fireworks display, beautiful and intense, but over far too soon. These stellar giants will live for only millions of years before exhausting their nuclear fuel and ending their lives in the violent explosions we call supernovae. Medium-sized stars like our Sun follow a more measured path. They burn their hydrogen fuel steadily for billions of years, maintaining a stable output of energy that can nurture planetary systems and perhaps even life. 6 billion years old, still has roughly another 5 billion years of stable burning ahead of it before it begins to evolve into a red giant star. The smallest stars, those with less than half the mass of our Sun, are the cosmic tortoises in this stellar race. They burn their fuel so slowly and efficiently that they can continue shining for trillions of years, far longer than the current age of the universe. These red dwarf stars will likely be the last lights burning in the cosmos, long after more massive stars have exhausted their fuel and faded away. Within these stellar nurseries, we also witness the birth of planetary systems. The same rotating disks that feed material to growing protostars also serve as the raw material for planet formation. Dust grains within these protoplanetary disks stick together, gradually building up larger and larger objects. First they form pebbles, then boulders, then asteroids, and eventually full-sized planets. The process is surprisingly chaotic and violent. Young planetary systems are dynamic environments where collisions are common and orbits can be dramatically altered by gravitational interactions. Some planets are ejected from their systems entirely, becoming lonely wanderers drifting through interstellar space. Others spiral inward toward their parent stars, creating the hot Jupiter planets that have surprised astronomers with their existence. The chemical composition of these protoplanetary disks determines what kinds of planets can form. Close to the central star, where temperatures are high, only rocky materials can condense. This is where we find the terrestrial planets like Earth, Mars, Venus, and Mercury in our own solar system. Farther out, where it's cold enough for water and other compounds to freeze, we find the ingredients for gas giant planets like Jupiter and Saturn. But perhaps most remarkably, these stellar nurseries are also where the building blocks of life itself are forged and distributed. Complex organic molecules, the carbon-based compounds that form the foundation of all known life, are created in the warm, dense environments surrounding young stars. These molecules are then incorporated into planets as they form, seeding them with the chemical ingredients necessary for biology to emerge. Water, that most essential ingredient for life as we know it, is also abundant in stellar nurseries. It forms as ice on dust grains in the cold outer regions of protoplanetary disks and can be delivered to rocky planets through comet impacts. The water in Earth's oceans may have originally frozen in the depths of the molecular cloud that gave birth to our solar system, linking our planet's life-giving seas to the cosmic processes that created our Sun. The study of stellar nurseries has revolutionized our understanding of how common planetary systems might be throughout the galaxy. Nearly every star we observe shows signs of having formed with a protoplanetary disk, suggesting that the ingredients for planet formation are present around most, if not all, young stars. This has profound implications for the possibility of life elsewhere in the universe. As we observe these cosmic cradles with increasingly sophisticated telescopes, we're beginning to understand that star formation is not just a local phenomenon, but a galaxy-wide process that has been ongoing for billions of years. Waves of star formation sweep through the spiral arms of galaxies, triggered by gravitational interactions and the compression of gas clouds. Each generation of stars enriches the interstellar medium with heavier elements, making it possible for the next generation to form rocky planets and complex chemistry. The universe is gradually becoming more chemically diverse, more capable of supporting the complex structures and processes that we associate with life and consciousness. And so these stellar nurseries represent more than just the birthplaces of stars. They are the cosmic laboratories where the elements of complexity, beauty, and perhaps even consciousness are mixed and distributed throughout the universe. Now, we come to perhaps the most enchanting chapter in our stellar story, the birth of planetary systems. These cosmic nurseries don't just create stars, they craft entire worlds, sculpting the very stages upon which the drama of life might one day unfold. It's a process that transforms swirling clouds of gas and dust into organized families of planets, moons, and countless smaller bodies, each finding their place in the grand choreography of gravity. Picture, if you will, those early moments after a protostar ignites into a proper star. The surrounding disk of material doesn't simply vanish, it becomes a bustling construction site. Within this protoplanetary disk, as astronomers call it, lies all the raw materials needed to build worlds. Dust grains, no larger than particles of smoke, begin their slow dance of accumulation. At first it's gentle, electrostatic forces causing tiny particles to stick together like cosmic lint. But as these clumps grow, gravity takes over, pulling more and more material into ever larger aggregations. The process is surprisingly orderly for something happening in the chaos of space. Close to the young star, where temperatures soar high enough to melt rock, only the hardiest materials survive, metals and silicates that will eventually form the rocky terrestrial planets. Further out, beyond what astronomers poetically call the frost line, water freezes into ice, and suddenly there's much more material to work with. Ice-coated dust grains stick together more readily, growing into larger and larger bodies that can eventually capture the abundant hydrogen and helium gas floating nearby, forming the gas giants. This isn't a quick process by human standards. The formation of planets takes millions of years, proceeding through distinct stages that astronomers have pieced together through careful observation and elegant computer simulations. First come the planetesimals, asteroid-sized bodies ranging from a few kilometers to hundreds of kilometers across. These are the building blocks of planets, and their formation represents a crucial threshold. Once you have planetesimals, gravity becomes the dominant sculptor, and the real construction work begins. Some planetesimals grow faster than others, becoming what we call planetary embryos. These are the successful competitors in the gravitational game, sweeping up smaller bodies in their orbital neighborhoods and growing ever more massive. It's a somewhat violent process. Imagine cosmic billiard balls colliding at tremendous speeds, sometimes sticking together, sometimes shattering into fragments that must begin the accumulation process anew. The rocky planets form through this process of accretion and collision. Our own Earth, for instance, is thought to have formed from countless impacts over tens of millions of years. The heat generated by these collisions was so intense that the early Earth was likely a molten hellscape glowing red-hot against the darkness of space. The Moon itself is believed to have formed from the debris of one particularly catastrophic collision, a Mars-sized object striking the young Earth with such force that it ejected enough material to eventually coalesce into our familiar lunar companion. Gas giants follow a different path. Once a planetary core reaches about 10 Earth masses, it can begin capturing gas directly from the surrounding disk. This process can be remarkably rapid, perhaps only a few 100,000 years to build up the massive atmospheres of Jupiter and Saturn. The ice giants Uranus and Neptune likely formed closer to the Sun and were later scattered outward by gravitational interactions with their larger siblings. But planetary formation isn't just about the planets themselves. It's about creating entire systems, complex gravitational environments where moons can form around planets, where asteroid belts and comet reservoirs establish themselves in the leftover debris, where the delicate balance of orbits determines which worlds might be suitable for life. The habitable zone, that Goldilocks region around each star where conditions might be just right for liquid water, becomes particularly fascinating in this context. It's not just about distance from the star, it's about atmospheric composition, planetary mass, magnetic fields, and countless other factors that emerge from the planet formation process. Venus and Mars both lie tantalizingly close to our own habitable zone, yet their different formation histories led to dramatically different outcomes. Venus became a greenhouse inferno, while Mars lost most of its atmosphere to space. And here's where the story becomes even more remarkable. The formation of planetary systems appears to be incredibly common. Nearly every star we examine seems to host planets of some kind. The Kepler Space Telescope and other planet-hunting missions have revealed a galaxy teeming with worlds, hot Jupiters orbiting impossibly close to their stars, super-Earths larger than our own planet but smaller than Neptune, and countless other configurations that stretch our imagination. Some of these systems look nothing like our own. There are planets that orbit two stars simultaneously, worlds where it rains molten glass sideways, and tidally locked planets where one side faces eternal day, while the other endures perpetual night. The diversity is staggering, suggesting that planet formation is both robust and remarkably creative in its outcomes. Yet for all this diversity, there are underlying patterns, physical laws that govern how matter behaves in the presence of gravity, heat, and time. The same processes that built our Earth 4.5 billion years ago are still at work today in stellar nurseries throughout the galaxy, crafting new worlds around young stars, each with its own unique character and history. What makes this particularly poignant is the realization that we are intimately connected to this cosmic construction project. Every atom in your body, save for hydrogen, was forged in the nuclear furnaces of stars and dispersed into space when those stars died. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was scattered into the cosmos by stellar explosions and eventually incorporated into the swirling disk that formed our solar system. You are quite literally made of star stuff, as Carl Sagan so beautifully put it, but you're also made of planet stuff. Atoms that participated in the grand construction project that built the Earth, that witnessed the formation of the Moon, that survived the bombardment of asteroids and comets, that delivered water and organic compounds to our world's surface. This ongoing cycle of stellar death and rebirth, of planetary construction and destruction, ensures that each generation of stars and planets is enriched with the products of previous generations. The universe grows more complex with time, more capable of creating the intricate chemistry necessary for life. What began as simple hydrogen and helium in the aftermath of the Big Bang has evolved into a cosmos capable of crafting worlds where complex molecules can form, where atmospheres can develop, where the delicate conditions necessary for biology might emerge. So as you drift towards sleep tonight, perhaps you can feel that connection, the gentle pull of gravity that keeps you anchored to this particular planet, the warmth of stellar fusion that reaches across 93 million miles to keep our world habitable, the slow rhythm of cosmic processes that continue even now, building new worlds around distant stars, preparing the stages for stories we can barely imagine. As we near the end of our gentle voyage through the cosmic nurseries where stars are born, let's pause for a moment to consider something truly extraordinary. We've travelled from the vast, dark molecular clouds where stellar formation begins, through the violent beauty of supernovae that scatter life's ingredients across space, to the delicate dance of planetary formation around young stars. But there's one more chapter to this cosmic story that brings it all wonderfully, intimately home. You see, the story of stellar nurseries isn't just about distant clouds of gas and dust collapsing under gravity. It isn't merely about fusion fires igniting in the hearts of protostars, or even about the spectacular deaths of massive stars painting the galaxy with heavy elements. No. This story is also about you, sitting wherever you are right now, made entirely of materials forged in the nuclear furnaces of ancient stars. Every atom of carbon in your body, every molecule of oxygen you breathe, every bit of iron in your blood was created billions of years ago in the core of a star that lived, burned brightly, and died long before our sun was even a twinkle in a nebula cloud. The calcium in your bones was forged in stellar cores. The nitrogen in your DNA was scattered across space by dying stars. Even the hydrogen in the water you drink has been cycling through the cosmos for over 13 billion years, part of an endless celestial story of creation and renewal. This isn't just poetic language or fanciful thinking. It's literal truth confirmed by decades of astronomical observation and stellar physics. We are quite genuinely made of star stuff, as Carl Sagan so beautifully put it. The stellar nurseries we've explored tonight aren't just distant factories of cosmic creation, they're the very foundries where you were made, atom by atom, over the course of countless stellar generations. Think about that for a moment. The elements that make up your body have travelled unimaginable distances and experienced cosmic events of breathtaking violence and beauty. Some of the atoms in your hand right now may have been forged in the core of a red giant star as it swelled to enormous proportions. Others might have been created in the split second of a supernova explosion, when a massive star collapsed and then erupted with the energy of billions of suns. Still others could have been slowly cooked in the steady fusion fires of smaller stars over billions of years. These atoms didn't arrive here by accident. They were carried on stellar winds, swept up in shock waves from exploding stars, and gradually incorporated into new generations of stellar nurseries. Eventually, about 4.5 billion years ago, they found themselves part of the rotating disk of gas and dust that would become our solar system. Some condensed into the rocky planets, others into asteroids and comets, and still others eventually found their way into the complex chemistry that would give rise to life on Earth. But the connection goes even deeper than our atomic composition. The very processes that govern life on Earth mirror, in fascinating ways, the processes we see in stellar nurseries. Just as gravity pulls together diffuse clouds of gas and dust to create new stars, the fundamental forces of chemistry and biology organize simple molecules into increasingly complex structures. The same principles of energy flow, chemical evolution, and emergent complexity that we observe in the formation of stellar systems also guide the development of living organisms. Consider how a single cell divides and grows into a complex multicellular organism, with different parts taking on specialized functions. It's remarkably similar to how a protoplanetary disk develops distinct regions, with some areas forming rocky planets, others gas giants, and still others remaining as asteroid belts or cometary clouds. Both processes involve the gradual organization of simpler components into more complex structured systems. And just as stellar nurseries are sites of both creation and destruction, where some protostars successfully ignite while others fade away, life on Earth has always been shaped by cycles of birth, growth, death, and renewal. The carbon that makes up your body has likely been part of countless other living things throughout Earth's history. It may have been part of ancient algae in primordial seas, towering dinosaurs, delicate flowers, or mighty trees before becoming part of you. And someday it will continue its journey, perhaps becoming part of new life forms we can't even imagine. This cosmic recycling isn't limited to our planet either. The stellar nurseries we've explored are still active today, still forming new stars and planetary systems throughout our galaxy. Some of these new worlds may already harbour life, or may develop it in the future. The same stellar processes that created the conditions for life on Earth are playing out right now in molecular clouds scattered across the Milky Way. In regions like the Eagle Nebula, the Orion Nebula, and countless other stellar nurseries, new generations of stars are being born. Some of these stars will be similar to our Sun, eventually developing their own planetary systems. A few of those planets may find themselves in that perfect zone where liquid water can exist, where atmospheric conditions are just right, where the chemistry of life might take hold and flourish. It's a humbling and wonderful thought that the story of stellar nurseries is ongoing, that we're living witnesses to a process that has been shaping the universe for billions of years and will continue for billions more. We're not separate observers of this cosmic drama. We're active participants in it. Every breath you take, every heartbeat, every thought is part of the same grand story that began in ancient stellar nurseries and continues today in nebulae scattered across the galaxy. The elements flowing through your bloodstream right now connect you to every star that has ever lived and died, to every stellar nursery that has ever formed new worlds, to every planet where life might be stirring into existence. You are quite literally made of the cosmos, and the cosmos lives and breathes and thinks and dreams through you. This connection extends beyond just our physical composition. The energy that powers your body ultimately comes from our Sun, which is itself a middle-aged star formed in a stellar nursery about 4.5 billion years ago. The light that warms your face and enables photosynthesis in plants is the same nuclear fusion process we've discussed in stellar cores. In a very real sense, you are solar-powered, sustained by the same stellar fire that illuminates nebulae and drives the formation of new worlds. And when you look up at the night sky, you're not just seeing distant points of light. You're seeing your cosmic family tree, the stellar ancestors whose lives and deaths made your existence possible. Every star you can see with the naked eye has contributed in some way to the story of how the heavy elements necessary for life were created and distributed throughout the galaxy. The constellations that have guided human navigation and inspired countless stories are made up of stars at different stages of their lives. Some are young, hot stars recently born from stellar nurseries. Others are ancient giants nearing the end of their cosmic journey. A few may have already died, their light taking so long to reach us that we're seeing them as they were years or even centuries ago. Each represents a different chapter in the ongoing story of stellar evolution. Even more remarkably, some of the stars you see tonight may have planets of their own, worlds that formed from the same stellar nursery processes we've explored. Thanks to modern astronomy, we now know that planets are common throughout the galaxy. Nearly every star likely hosts at least one planet, and many have entire planetary systems as complex and diverse as our own. This means that the stellar nurseries we've discussed aren't just creating stars, they're creating entire worlds, perhaps some with conditions suitable for life. The same gravitational collapse that forms a new star also creates the disk of material from which planets emerge. The same heavy elements forged in previous generations of stars become the raw materials for rocky planets, organic molecules, and potentially living organisms. So as we drift towards sleep tonight, carried along by the gentle rhythm of our breathing and the steady beating of our hearts, we can take comfort in knowing that we're part of something vast and beautiful and ongoing. The stellar nurseries that gave birth to the elements in our bodies are still active throughout the galaxy, still weaving new chapters in the cosmic story of which we are part. We are the universe becoming aware of itself, stardust organized in such a way that it can contemplate its own origins and wonder at the beauty of stellar nurseries scattered across the cosmos. In our curiosity about these distant regions of star formation, in our awe at the processes that create new worlds, we are participating in the universe's own journey of self-discovery. And perhaps that's the most beautiful part of this story. The stellar nurseries we've explored tonight continue their ancient work of creation, forming new stars, new worlds, new possibilities for complexity and perhaps even consciousness to emerge. Somewhere in the galaxy, in a nebula we might never see, the materials for future life are being forged in stellar cores and scattered by stellar winds, beginning their own long journey toward worlds and wonders we can only imagine. Sweet dreams, fellow travellers of the cosmos. As we reach the end of our cosmic journey through stellar nurseries, we find ourselves part of an even grander tapestry, one that weaves together not just the birth of stars, but the very essence of existence itself. You see, these stellar nurseries don't simply create distant points of light in the night sky. They forge the fundamental building blocks of everything we know and love, including you and me. Consider for a moment the remarkable fact that every atom in your body, save for hydrogen, was created inside the heart of a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it emerged from the nuclear furnaces of massive stars that lived, died, and scattered their enriched remains across the cosmos billions of years ago. Carl Sagan captured this beautifully when he said we are made of star stuff, but it's more than poetic metaphor, it's literal truth written in the periodic table of elements. The stellar nurseries we've explored tonight are not just factories of star formation, they're recycling centres of cosmic proportions. When massive stars reach the end of their lives and explode as supernovae, they don't simply vanish into the void. Instead, they seed the interstellar medium with heavy elements, creating new pockets of enriched gas and dust that will eventually collapse to form the next generation of stars. It's a beautiful cycle of death and rebirth, destruction and creation, playing out across millions of years in the vast theatres of space. This process has been ongoing for over 13 billion years, each generation of stars adding more complexity to the cosmic recipe. The first stars that formed after the Big Bang were made almost entirely of hydrogen and helium, the simplest elements in the universe. But as these primordial giants lived and died, they enriched their surroundings with carbon, nitrogen, oxygen, silicon, and countless other elements. Subsequent generations of stars inherited this chemical wealth, allowing for the formation of rocky planets, complex molecules, and eventually, life itself. The implications of this cosmic recycling program are profound. Every stellar nursery we observe today is built upon the ashes of countless previous generations of stars. The dust grains swirling in these nebulae contain the remnants of ancient suns, their atoms having journeyed through multiple stellar life cycles before finding themselves in a new protoplanetary disk, perhaps around a young star, not unlike our own sun was 4.5 billion years ago. This perspective transforms how we view our place in the universe. We're not separate from the cosmos, observing it from the outside. We are the cosmos, temporarily organized into conscious beings, capable of contemplating our own stellar origins. The very neurons firing in your brain as you listen to these words are made from elements forged in the hearts of dying stars, arranged in patterns complex enough to experience wonder, curiosity, and perhaps even sleepiness. The stellar nurseries also remind us of the incredible patience of the universe. The processes we've discussed tonight unfold over timescales that dwarf human experience. A typical star formation region might remain active for millions of years, slowly converting gas and dust into new stellar systems. The massive stars that drive much of this activity live fast and die young, but their deaths trigger new waves of star formation that can continue for tens of millions of years. Yet despite these vast timescales, stellar birth is happening right now all around us. As you drift towards sleep tonight, new protostars are igniting their nuclear fires for the first time. Planetary systems are taking shape in accretion disks hundreds of light years away. Somewhere in the Orion Nebula, a grain of dust is beginning its journey toward becoming part of a new world, perhaps one that will someday harbour life. The story of stellar nurseries is ultimately a story of connection, of the invisible threads that link every atom, every molecule, every living thing to the grand narrative of cosmic evolution. We exist because stars lived and died long before our solar system formed. We breathe because ancient supernovae scattered oxygen across the galaxy. We think and dream and wonder because billions of years of stellar alchemy created the elements necessary for complex chemistry, and thus for life. This connection extends beyond our individual existence to encompass all life on Earth. Every tree, every bird, every microbe swimming in a drop of pond water is made from the same stellar ingredients, assembled through the same cosmic processes that created you. We share not just a common planetary home, but a common stellar ancestry that stretches back to the very first stars to light up the primordial darkness. As we look toward the future, stellar nurseries will continue their ancient work, creating new stars and planetary systems long after our sun has exhausted its fuel and our Earth has become uninhabitable. The universe is still young, cosmically speaking, with trillions of years of star formation ahead. New stellar nurseries will form, new elements will be created, and perhaps new forms of life will emerge to contemplate their own origins under alien skies. So, as you settle into sleep tonight, carry with you this gentle reminder of your cosmic heritage. You are not just a resident of Earth, but a child of the stars, born from the same processes that light up the night sky. The stellar nurseries scattered throughout our galaxy are not distant alien places, but the very wombs from which you and everything you hold dear ultimately emerged. In the quiet darkness of your bedroom, remember that you're travelling through space on a rocky world orbiting a middle-aged star in a galaxy filled with stellar nurseries creating the next chapter of the cosmic story. It's a story in which you play a small but meaningful part, a brief but beautiful arrangement of star stuff that has somehow learned to contemplate its own existence. We hope you enjoyed the story tonight. Before we end our journey, can you comment where you're watching from? Also, let us know what time it is there. We love to hear people joining us from around the world to be a part of our community. Also, don't forget to leave a like and subscribe if you enjoyed this story. Good night, fellow space explorer.